All right, so let's look at another example. This one's kind of already done for us, so we won't waste too much time on it, but just so you can see it. 4 random samples, so this is going to be important again a little bit later, but 4 different samples were taken from viewers of ABC, CBS, NBC, and PBS news programs, and they were asked their political affiliation. So obviously what they're wondering here is, well, likely, is that, is the political affiliation distribution of ABC different than some of these other stations, right? Does this sample provide significant evidence that the distribution of political affiliation is different for 2 or more networks? If there is a significant difference, conduct a post hoc analysis to determine where the differences may occur. All right, so first, skip the P step. The null is that the true distribution of political affiliation is the same for all 4 networks, versus the distribution of political affiliation is not the same for all viewers of each of these 4 networks. Assumptions and conditions. We had 4 random samples. All 4 sample sizes are less than 10% of the populations of their respective populations. Expected counts. So this is where the calculator is going to really save us time. If I wanted to calculate the expected counts for this cell, I would simply take 70 times 40 divided by 300, right? To find the expected counts, you take the row total times the column total divided by the grand total. That's that number. I'd have to do that for every single one of these cells. It would be very time consuming. But when we run the program on our calculator, it calculates those for us. So let's just do that, okay? I've already put the matrix in our calculator. Remember, you hit this little button here to get the matrix, and then you put in the right size. I'm going to store it into OBS. That's the only input that you need for your calculator. Menu, statistics, stat tests, two-way test, put in your observed matrix. Now you want to see the expected counts, hit the vars key. Go to your expected counts. There they are. Okay, so I'm going to copy those down into my table, and I'm going to say all the expected counts are greater than or equal to 5. See the chart. Again, you have to have it on your chart, on your paper somewhere. Okay, and the samples are independent. I got multiple samples, so I check the 4th condition. This is a chi-squared test for homogeneity. Degrees of freedom. 4 minus 1 times 3 minus 1. That is 3 times 2, also known as 6. Or, just look at your computer output, 6 degrees of freedom. Okay. Test statistic, chi-squared, p-value, copy those down. Again, we don't have to show the formula if we don't want to, because we name the test. Our p-value is much less than 0.05, so we're going to reject the null. Means we have convincing evidence that the true distribution of political affiliation is not the same for these 4 networks, for the viewerships, population viewerships of these 4 networks. I could probably word that a little better, but it's good enough. All right, so now the post hoc analysis. So now we know there's a difference, but where is the difference? And you can see it's not quite so easy to just glance at this and see. For example, you see a difference of 4 right here. Well, I see a difference of about 5 right there. But, those are the same differences, but they have different contributions to the chi-squared component because the counts are the same. This is almost a half of difference, whereas this is a smaller difference in terms of percentages. So it's kind of hard to evaluate, but you can kind of see big increase in much more observed than expected. So CBS probably likes conservative viewers, or it's a lot more conservative viewers. NBC has a lot less. So maybe NBC is more liberal. MSNBC, they talk about that being one of the more liberal stations nowadays. But it's hard to compare exactly. So let's go to that the component matrix and see if that can help us a little bit. Go to your vars key, comp matrix. And all right, so here's the comp matrix. So the chi-squared test statistic was 30.4. So if you were to add up all of these 12 cells, it would add up to 30.4. So which ones are the biggest contributors? I see a 13.8, I see a 4.2, and I see a 3.2. So these are the three spots where we had the biggest differences, biggest contributors to the chi-squared test statistic, not the biggest differences. Now these are always going to be positive, so this doesn't tell me whether there was more observed or less. So we need to kind of describe that, but that is these three cells right here. So perform a post hoc analysis, and I'm sorry, I don't really like my answer here. I don't like it because I don't have specific numeric evidence. I need to rewrite it, I'm sorry. But basically I said CBS seems to have a small number of conservative viewers and more moderate viewers than expected. NBC also has less conservative viewers than expected and has the largest contribution to the chi-squared test statistic. But it doesn't say anything about any specific numbers. It doesn't talk about the comparison of expected versus observed, nor does it comment on these things. Yeah, so I guess I'm just going to say you guys need to do better. And that's probably a terrible teaching because, I should demonstrate better, but again, it's not likely that you'd see this type of question on an AP test, but if they ask for it, you need to give more than this. You need to compare observed and expected counts. You need to cite the actual contribution to the chi-squared test statistic and really just take more time to answer that question. All right. All right. So now let's talk about the chi-squared test for independence. It's going to look almost exactly the same. Almost. There's going to be kind of just a couple slight differences. First of all, this is a test, the chi-squared test for independence, is a test to see if there's an association between two categorical variables in a single population. Sometimes this is called the chi-squared test for an association. So these are the same tests. You can use these interchangeably, whichever one you prefer. But this is a test if you have two variables from a single population. Homogeneity was one categorical variable across multiple populations. That's basically the difference. Okay? Mechanics are the same. The only thing that's different is how we word the null and alternate hypothesis. That's pretty much it. Well, also there's no fourth check because we only have one sample. So the checks are random. Your one sample needs to be random. Your one sample needs to pass the 10% condition. All your expected counts need to be greater than or equal to 5. That hasn't changed. There's no fourth check because you only have one sample. You can word your hypotheses two different ways. You could use it using the word association or the word independence. If you use association, which is what I prefer, you say the null is going to be that there is no association between two categorical variables in the population of interest, versus the alternate that there is an association between those two variables in the population of interest. Alternatively, you could say the two categorical variables are independent, versus the alternate that the two categorical variables are not independent. The only thing you need to be careful about is, no association, yes association, yes independence, no independence. These are the opposite of synonymous. They're the same, they mean the same thing, but they're negated of each other, okay? So an association is the same as not having independence. So however you word it, you just need to make sure you're clear about that, I guess. Same chi-squared statistic, same degrees of freedom. We still look for the area to the right. It's really pretty much the same. This slide here, this section here highlights the differences between them. So put a star by this. Actually, put a star right by this one right here. Boom. Boom. Okay, so although these tests look the same, they answer a different question. Homogeneity analyzes whether the distribution of a single variable is the same for several populations. Independence analyzes whether two categorical variables are associated in a single population. So really the question is, do you have a single sample and it's a test for independence, or do you have multiple samples? It's a test for homogeneity. That's it. Just look at the question, read it, because you're not going to be able to tell by looking at the table. The tables are all going to look exactly the same. Also, if it's an experiment, it will always be a test for homogeneity. Okay? All right. So we got one example. Almost done. Hopefully maybe just one more video.